Many of the numerical methods that we will study in this class will involve quite a bit of linear algebra. So in this lecture, we're going to review just a few key concepts from linear algebra that you're probably already familiar with. A square matrix, denoted bold-faced A, has a determinant, and that determinant can be found using a formula like this. It's a weighted sum of the minors of the elements of the matrix. Aik is an element in the ith row and the kth column. The minor of a matrix is the determinant of a submatrix found by deleting row I and column k. This term in the middle here selects whether each term is either added or subtracted from the sum by being either a -1 or a 1. This sum only needs to be taken for one row in the matrix, and it's therefore easiest if we choose a row that has the most zeros in it, because that will have the fewest terms in the sum. We'll show what this looks like for a 3 by 3 matrix. For a 3 by 3 matrix with no zeros, we'll have 3 terms in the sum. So if we use this formula for the first row, we start with the A11 term, and we eliminate the first column and the first row from the matrix. And then we find the determinant of the remaining submatrix. That's the minor of the 1, 1 element. This term is -1 to the 2, or -1 squared, which is 1. Next, we find the minor of the submatrix created by eliminating the first row and the second column. So that's this matrix. And this term now takes the sign -1. And we can do the same thing, eliminating the first row and the third column to form the minor of the 1, 3 element. This one is added instead of subtracted. This procedure for finding the determinant of a 3 by 3 matrix requires also finding the determinant of 3 2 by 2 matrices. But the determinants of the 2 by 2 matrices are very easy to find. In this case, for the 1, 1 minor, the determinant is A22 times A33 minus A23 times A32. This result can be arrived at by using the same formula that we used for the 3 by 3 matrix. Similarly, the determinant of 3 by 3 matrices can be found using a relatively easy to remember pattern. It's the sum of the product of the diagonals going in one direction minus the sum of the product of the diagonals going in the opposite direction. For matrices larger than a 3 by 3, I don't recommend doing this by hand at all. I would use MATLAB and use the det function. The determinant can be easily found by defining the matrix A in MATLAB and calling it as the argument to the det command. Here are some important properties of determinants that we'll make use of throughout the semester. The determinant of the product of any two matrices is the product of their determinants. And the determinant of a matrix is equal to the determinant of the transpose of that matrix. For matrices that are either lower triangular, upper triangular, or diagonal matrices, meaning they have zeros above the diagonal, below the diagonal, or both, then the determinant is simply the product of the diagonal elements, A11, A22, A33, etc. If any of the rows or columns of the matrix are not linearly independent from other rows or columns, then the determinant of the matrix is 0. We call matrices like this singular. A matrix that has a 0 determinant is called a singular matrix. One important property of singular matrices is that they do not have an inverse. That is, there's no matrix that you can multiply by a singular matrix to obtain the identity matrix. One application of using matrix determinants is called Cramer's rule. Cramer's rule is a method for solving linear algebraic equations. If we have n unknown values, x1, x2 through xn, and we want to solve for this x vector, a set of linear algebraic equations, we could write those equations in matrix and vector form and use Cramer's rule. Cramer's rule requires computing n plus 1 determinants that are denoted here with the symbol delta. Delta sub k is obtained by taking the determinant of a matrix where we replace column K in the matrix with the vector B, where B is the vector of values on the right-hand sides of the equal signs in our linear set of equations. The determinant delta is the determinant of the original coefficient matrix A. Cramer's rule says that each of the x's can be found by dividing delta K by delta. Another application of matrix determinants that you may be familiar with is when solving the matrix eigenvalue problem. The matrix eigenvalue problem finds the eigenvalues lambda and the eigenvectors v for any square matrix A that satisfies this equation. For an n by n matrix, there will be n eigenvalues and n eigenvectors. Eigenvalues can be repeated. Solutions to the matrix eigenvalue problem can be used to also solve sets of linear ordinary differential equations. The solution to the matrix eigenvalue problem is the set of n values of lambda and their corresponding eigenvectors v. Notice since the eigenvectors v appear in the products on either side of the equal sign here, each of those eigenvectors v can be multiplied by an arbitrary constant and still be a solution to the matrix eigenvalue problem. What that means is that the direction of the eigenvector in n space is what's important and not its magnitude or its length. One way to solve the matrix eigenvalue problem is to first rewrite the equation by subtracting lambda v from AV and setting the result equal to the null vector 0. Then we factor out the eigenvectors, and we establish that this can only be the case when either the eigenvector is 0 or the determinant of A minus lambda I is 0. This represents a trivial solution. We want to find the solutions where the determinant of A minus lambda I is equal to 0. We can do this by writing equations for the determinant of the matrix A minus lambda I. If we use the formula for the determinant, we'll be taking a sum of terms that contain products of each of the elements of this matrix when we find its determinant. That sum of products will be a polynomial in lambda, and it will have order n. Since that determinant must be equal to 0, the roots of that polynomial represent the solutions, or the eigenvalues, lambda. Once each of the eigenvalues lambda is known, then we can take those eigenvalues and plug them back into this equation to solve for the corresponding eigenvectors for each eigenvalue. When finding the eigenvectors, we will have n equations for the n elements of the eigenvector v, and we can do that for each of the eigenvalues lambda. That will give us n pairs of lambda, the eigenvalues, and v, the eigenvectors. We should expect when solving this last equation to find the eigenvectors that the equations that we write will not be linearly independent, leaving one degree of freedom. That remaining degree of freedom is the magnitude of the eigenvector v. Remember that in the matrix eigenvalue problem, the magnitude of v is arbitrary. That is, v can be multiplied by an arbitrary constant. So it's no surprise that we get to choose the magnitude of v. By definition, the matrix A minus lambda I is singular because we said that its determinant must be equal to 0. And that's why v can be multiplied by an arbitrary constant.